Hello class, welcome to this lesson on 6.4. This is actually the last section in the chapter, so we're actually going to wrap this chapter up. We're going to be talking about the Central Limit Theorem today. So the first thing we want to address is how can we use the Central Limit Theorem to solve problems involving the sampling distribution. The learning goals include to use the Central Limit Theorem to solve problems involving the sample means for large samples. So the vocab we're going to be including today is the sampling distribution of sample means, the sampling error, the standard error of the mean, and the central limit theorem. Alright, so in addition to knowing the behavior of individual values x for a population, sometimes we're interested in the behavior of the mean of a sample taken from a population. So traditionally, we were concerned with just data that we collected and then determining whether it follows a normal distribution, right? Or we draw the distribution. This time we're interested in taking a sample from a population. Okay, so let's say that we're interested in blood triglyceride levels. So those are levels of fat that are in the blood. So let's say we have this population of subjects, right? Let's say all the patients in a particular hospital, and that is our population, okay? Suppose. So listed within this big box of this population, right, this hospital, you have a bunch of numbers, a bunch of blood triglyceride levels. And these represent the triglyceride levels of the different patients, right, in the hospital. So what we're going to want to do is we're going to want to take a sample, because it's not possible to do every single patient, right? Especially if you're talking about the entire U.S. if you're interested in a big study of an entire country. But in this example, we have a lot of patients, and we don't want to sample every single patient to draw a conclusion from the data. So what we're going to do is we're going to randomly take some samples. Okay, so let's say I take this sample here, and that will be my sample of 4 patients. And then I'm going to want to take another sample of 4 patients randomly, just to make sure that the data kind of agrees, and I'm going to take multiple data points that way. All right, so let's say I did that, and then let's say I took another sample of, say, 4 right there, right here, etc., right? And you reuse the same patient as long as you're doing this in a random fashion. So you want to randomly select your samples. Okay, so in this case I took 3 samples. The sample size is 4. All right, let's assume that based off of all of this data for all the patients, that the population mean is 170 milligrams per deciliter. So if we were to average up all of these numbers, we're going to get 170. Now assume that if we graph this, we get something that is skewed to the left. Okay, so for example, if we're talking about the blood triglyceride levels in patients that are sick, they're probably going to be on the high side, right? So we'll assume that the data is skewed to the left, which means that we have a graph that looks like this. Okay. Now this graph is known as the distribution of individual values. Okay, so this is just the original distribution. So this is the graph of x, right? The distribution of x. All right, so now suppose now that we're going to take those samples, right? Let's say that first sample that we took was this guy, and then the other one was 162, 165, 129, 143. So let's say those were a couple of our samples amongst other samples. Okay, so then for the samples, what we're going to do for each sample is we're going to average the numbers in that sample. And that's going to be called our sample mean, right? X bar. So the X bar for our first sample is 150. I just simply add them up, divide by 4. The X bar for my second sample is 149.75. And I continue doing this, and I continue doing it for multiple samples until I get a distribution that I can graph. Okay. Now this distribution is going to be called the sampling distribution, otherwise known as the sampling distribution of sample means. Now this time we're not graphing x, we're graphing x bar. So we're graphing the average blood triglyceride level in this case, rather than an individual triglyceride level. So if we were to graph the triglyceride levels based off of our samples that we took, we'll get something that looks kind of like this, something that's normally distributed. We'll talk about shape in a little bit. But the main thing you want to know is that this curve, based off of the sample means, is called the sampling distribution of sample means. So the sampling distribution of sample means is a distribution that uses the means computed from all possible random samples of a specific size taken from a population. So in our example, we took some samples, but we did it for a sample size of 4. But we would have to do it for every single possible sample size of 4. So every single possible sample with size 4. And then we collect all those sample means, and then we graph those. Okay, so if the samples are selected randomly, the sample means will most of the time not really be equal to the population mean. So for example, in the previous example, the mean was 170, and we did the sample mean and we got about 150. So most of the time they're not going to be equal to the population mean. So this is the example that I mentioned earlier. Our first sample mean was 150, but our population was 170. So that means we got a difference of negative 20. So we were 20 under the population. Now this difference or error is known as the sampling error. So the sampling error is the difference between the sample mean and the population mean. And this is due to random sampling. So if you randomly select a particular sample, there's going to be a random chance that it's going to be below or above. That's just the nature of sampling. So the sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. So since you're taking a sample that is by definition smaller than the population, you're obviously not going to represent every single person in the population, so there's a good chance you're going to fall short. You're going to underestimate or overestimate the mean. So what is the properties of the distribution of the sample means? So that was that one curve that we did earlier. So the mean of the sample means has to be equal or will be equal to the population mean. The second property is that the standard deviation of the sample means will be smaller than the standard deviation of the original population. And it will be equal to the standard deviation of the population divided by the square root of the sample size. All right, so the symbol for the mean of the sample means is mu x bar. Okay, so mu stands for mean, and x bar stands for the sample mean. So this is the mean of the sample means. And this is going to be equal to the original population mean. Okay, the mean of the individual data. All right, the standard deviation of the sample means, the symbol for that is lowercase sigma x bar. And that's going to be smaller than the original standard deviation because it's going to be the original standard deviation divided by the square root of n. So therefore it's smaller because you're dividing by a number on the bottom. So these are a couple of properties. We're going to actually illustrate these two properties with an example, a very specific example. So let's suppose a professor gave an 8-point quiz to a small class of 4 students. So very small class, so let's assume that the 4 students constitute the entire population of this professor's class. All right, very small class. And this is just to make the results easier to quantify. So now the individual results of the population, let's say that these students scored 2, 6, 4, and an 8. So those are the 4 students and their scores. So this is my population. So we're going to do the population mean, so we're just simply going to average those numbers together. And you're going to get 5 for these. So the 5 is the average score of this population. All right, so next what we're going to do is calculate the standard deviation of this population. The standard deviation is the spread of these scores, okay? So there's the formula to do it is a square root, and then you take each number. So for the first number is 2, then you take away the average, which is 5, and then you square it. And you do that for all the numbers. And then once you do that, you square them, add them up, divide by how many numbers you have. In this case, we have 4 numbers, right? So that's this guy right here. And then you take the square root, and we get 2.23. So now that's the standard deviation. And we went ahead and did the graph. So the graph, this is the graph this is the distribution of the student scores. So one student scored a 2, 4, 6, and 8. So this distribution is known as a uniform distribution, and that's because all these scores are the same. So it's all the same height. So notice it's not a normal distribution, it's just a uniform. So now we know the population is 2, 4, 6, and 8. So what we're going to do now is we're going to take samples of that population with replacement. So that means if I choose a particular student, I'm going to, a particular score, I'm going to put that score back in, and then I'm going to randomly select another set of scores, which means I could have repeats here. So I'm going to do a sample size of 2 because I have a very small population of 4, so I'll just take 2 numbers randomly. What we're going to do is write out all the possible ways of taking sample sizes of 2. So you can get 2 2s, you can get a 2 and a 4, 2 and a 6, 2 and an 8, all the way to getting 2 8s. Okay, so these are all my possible samples that I could take for a sample size of 2. All right, so now what we're going to do is we're going to do the sample mean of each of those samples. Okay, so those are my samples. I got 16 samples in total. So the x bar for the first sample is 2, and then 3, and so on. So 2 plus 2 divided by 2 is 2. The next one, 2 plus 4 divided by 2 is going to give you 3. So that's how I get the averages of each of those samples. Okay, so now that I did these sample means, I'm going to do the mean of the sample means. So I'm going to take the average of all of those means. So all of these means I'm going to take the average of. So I'm going to add them up and then divide by 16 because I got 16 of them. And I'm going to get a mean of 5. That sounds very peculiar, right? We got the same exact mean that we got from the original population, which is a very interesting finding. So now the next thing is the standard deviation of the sample means. So to find the standard deviation, all you got to do is kind of do what we did before. You're going to take each of these values. So the first one is 2, and then you're going to subtract by the mean that we found here. Okay, and then you're going to keep doing that. So we got 3, and then 5, and then you're going to square those results and then add them together, divide by 16, take the square root, and you get your standard deviation. Now notice our standard deviation here is smaller, right? This standard deviation right here, sigma x bar, is actually smaller than our original population standard deviation. And that's because what we said earlier, right? The property has to be smaller. So let's go ahead and write down these two properties again. The first property is that the mean of the sample means is equal to the population mean, which is 5. It worked out. The second property, the standard deviation of the sample means is smaller than the original standard deviation. And it's given by sigma divided by square root of n. The original sigma was 2.23-ish. Divide that by the square root of 2 because their sample size is 2, and we get our exact same standard deviation. So basically we can calculate this standard deviation here by just using this formula. We don't have to actually calculate all of this in order to get the standard deviation. We can use that simple formula and we'll get the exact same result. All right, so now what we're going to do is we're going to actually draw a histogram of the sample distribution. All right, so what we're going to do is we're going to list out all the means, all the possible means. So all the possible means are 2, 3, all the way to 8, right? So we got 2, 3, 4, 5, 6, all the way to 8. So we have 8, let's see, 1, 2, 3, 4, 5, 6, 7 different means from 2 through 8. And so we got 1, 2, we got 2 3s, we got 3 4s, we got 4 5s, we got 3 6s of means. So I'll illustrate one of these for you. So for the mean of 5, we have 4 of them. 1, 2, 3, 4, 5s, and therefore we said that there's 4 of them. Okay, so the frequency is 4. So now what we're going to do is we're going to take this distribution, we're going to graph it. Okay, using the same distribution, If we graph it, well, okay, well we have 4 5s, right? So that's why there's 4 5s there. We have 3 4s in the distribution in the table, and so we get something that that is approximately a normal distribution. So this is very important that this distribution is approximately normal. This is a very interesting finding, and we're going to actually talk about this. This is going to lead to the central limit theorem. So in summary, if all possible samples of size n are taken with replacement from a population, the mean of the sample means mu x bar equals mu. The standard deviation sigma x bar equals the population standard deviation divided by the sample size n. Now there's a special name for the sigma x bar. It is known as the standard error of the mean, shortened as SE for standard error. So if you hear me refer to this as the standard error, that's what I mean. The standard error is just the standard deviation of the sample means in this example. Okay. So a third property not mentioned is the shape of the distribution. So the original distribution we said was uniform. The sampling distribution, however, which we graphed earlier, is normal. So this is uniform, and this is approximately normal. So this means that even if you don't have a distribution that is not uniform originally, if you take the samples of that population and then you take and then you do the means and graph those, you're going to get something that's approximately normal. And this approaches a normal distribution and is based off of the central limit theorem. So as we take samples, the greater the sample size, in this case we had a sample size of 2. If we did a sample size of 3 and so on, the more closely the distribution resembles a normal distribution. So the central limit theorem, as the sample size n increases without limit, which means as n approaches infinity, the limit of infinity, that's what's called a limit, central limit theorem. The shape of the distribution of sample means taken with replacement will approach a normal distribution. As previously shown, the distribution will have a mean of mu and a standard deviation or standard error, in this case, of sigma divided by square root of n. All right, so this is true even if the original distribution is not normal, okay? If the distribution is not normal, the original, then a large sample size must be taken for the curve to be really close to the normal distribution according to the CLT, the central limit theorem. What is this cutoff? The sample size has to be greater than or equal to 30 in order for the results to be valid, okay? So if the original distribution is not normal. If the original distribution is normal, then it does not matter what the sample size is. It can be very small, it could be small or large, and you'll still be able to apply the central limit theorem. All right, so let's talk about how to compute z-scores. Since we know now that the sampling distribution as sample means will be normal distribution or approximately normal, this means we can actually compute z-scores. So remember that for an original distribution x, the formula for the z-score is x minus mu divided by sigma. So the formula for the sampling distribution is going to be very similar. Notice that the template is very similar. We have the x in here, but now this becomes x bar because we're doing it for x bar here. Whereas for this guy, we were doing it for x. So instead of doing it for x, we're doing it for x bar. And then instead of just a regular mu, we're doing a mu x bar. Instead of a regular sigma, we're doing a sigma x bar. So that's the only difference in the formulas. However, remember that we mentioned that the two properties, right? That mu x bar is equal to mu. So therefore, I can replace this with mu. And then the second property is that the sigma x bar, the standard error, is equal to sigma over square root of n. So I can replace that with sigma over square root of n, which is what we're going to do now. And there's our new formula for the sampling distribution z-score. So we're going to be using that z-score for the central limit theorem. All right, so now because notice that the sigma is divided by a number, right, the square root of n, this means that the standard deviation is smaller. Standard deviation that is smaller means less spread. Less spread, so if it's less spread out, this means that it's going to be skinnier. It's gonna be spikier, okay? So it's gonna be skinnier, or you can think of it as spikier, less flat, okay? So less spread means spikier or skinnier. More spread means flatter, right, or wider. So notice how skinny this bell curve actually looks. All right, so let's look at an example. So A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. All right, so first off, you wanna notice that they're asking for the probability that the mean of the number of hours is greater. This means that they're asking about the x bar. Mean is x bar, okay? So they're asking for the probability that the x bar is greater than 26.3. This means that we're shading to the right when we do our curve. Now, this also means that we're looking at a central limit theorem problem. We're looking at a central limit theorem problem because we're talking about x bar, not x, okay? So every time they're referencing the probability of x bar, central limit theorem, which means that for step 1, we need to draw a skinny normal distribution, which I drew here. The mean of that distribution is given by mu, and that's equal to 25. Okay, so let's go ahead and zoom in on that. So the mean is 25. How do we know that the mean is 25? Well, it says that assume that the variable is normally distributed and the standard deviation is 3 hours. So this right here is my sigma, and they said that they reported that the ages of 2 and 5 watch an average of 25 hours of television. So that's the average population for like the entire population of children between 2 and 5. So that's my mu. Okay, so we know that the mu is 25 and the standard deviation is 3. However, when we do this curve, we're doing it based off the sigma divided by square root of n. So just keep that in mind. We're going to be using the formula for that. All right, so first step, draw the skinny normal distribution and shade the area we want to the right. Greater than means to the right, so we shade here to the right of 26.3. Step 2, convert the x bar value to a z value. So we're going to be using the central limit theorem z-score for this, okay? So therefore we plug in the numbers. We said that sigma was equal to 3 earlier. The sample size, it says you're looking at 20 children, so my sample size is 20 there. So therefore I plug in 20 for my sample size. All right, we go ahead and plug in those numbers. We get a z-score of 1.94. Once we do that, we're going to find the corresponding area for the z value using the standard normal distribution table. This is the z table that I pass out that you reference in class. You can easily do a web search for the standard normal distribution table. They're very commonly spread out in the literature and in the web. All right, so if we want to find the area to the right, remember that we need to do, if you want to find an area to the right, you got to do 1 minus the area to the left. The table gives you by default the area to the left. So therefore we do 1 minus the table value. And this value is the value from the table, the z table. If we look that up, we get 0.9738. And then we got to do 1 minus, and we get our answer. We're going to show you the table just in case you want to see how that looks like. Remember, we're looking at 1.94. So we look at 1.94 on the z chart. Remember, the z chart just gives you the area to the left, which is why we need to do the 1 minus to get the area to the right. All right, so we need to look at 1.96. I believe it was 1.96. Let's double check. Yeah, 1.94. So we have 1.94, which means that our area is 0.9738. So just as a refresher, in case you forgot how to actually locate those on the Z chart. All right. So let's look at one more example. So the average time spent by construction workers who work on weekends is 7.93 hours over 2 days. Assume the distribution is approximately normal and has a standard deviation of 0.8 hours. Find the probability that an individual who works at that trade works fewer than 8 hours on the weekend. And then part B, if a sample of 40 workers is randomly selected, find the probability that the mean of the sample will be less than 8. All right, so let's look at the first problem. Notice that for part A, they're asking for the probability that an individual who works at that trade works fewer than 8 hours. So they're not looking at a sample mean. They're not looking at a sample. They're looking at a particular individual, which means that this is not a central limit theorem problem, okay? So this is an X problem, not an X bar problem. So therefore, for step one, we are not going to draw a skinny normal distribution. We're going to draw a normal fat one, okay? We're just going to draw the one that is less spikier and more wide, okay? This is because we're not doing the central limit theorem. And therefore, we're not using the original formula for Z. We're using the other formula for the Z, the traditional formula, x minus mu over sigma. Okay, so then remember, so they told us that the mu, this is my mu, is 7.93. They said that the standard deviation is 0.8. And therefore, go ahead and plug those in for mu and sigma. My x is what they're looking for. They're interested in the 8 hours. So this is my x. Okay, so since they're saying that we want it to work fewer than, then this means that x is less than 8, which means we are shading to the left here, okay? So therefore we shade to the left on my curve. All right, so now that we find the Z value and we plug those numbers in, we're going to find the area to the left using the table. Now, since the table gives you the area to the left by default, this means that we just look it up and we got our answer. So we're going to look up 0.09 in the normal distribution table. So my Z-score is 0.09, which means that this is my area, 0.5359. All right, which is exactly what we have here. All right, so for part B, now this question involves the probability that the mean is a certain number. So if we go back to the original problem, this is saying if a sample of 40 workers is randomly selected, find the probability that the mean of the sample will be less than 8. So this is a sample mean problem, which means that this is an X bar problem. So this is saying that the X bar is less than 8. So therefore, X bar means central limit theorem. Okay, so this time we're going to draw a skinny normal distribution. So compare this to the original distribution. See how the step one, or the first one, is less spikier, and the part B is more spikier, and skinnier. Then we do the Z value, which means we need to use the sigma over square root of n formula. We go ahead and plug those numbers in. They mentioned that the sample size was 40 in the original problem. So if a sample of 40 workers, so that's my n. All right, so we go ahead and plug those in and we get our Z-score of 0.55. Then we look up the area to the left, so we'll go ahead and show you that real quick. So we have 0.55, which means our area is 0.7088. So let's go back to our problem, and that's exactly what we got. All right, class, that's it for the lesson. I hope you took a few things from this video, and I will see you in the next one.